Our project took place in Devil's Half Acre, which is in the southeastern portion of the Fundy National Park. Recently, it has become a point of interest for Fundy National Park staff, as they believe that it has the potential to provide adequate hibernaculum for native bat species. Since these crevasses are still moving and shifting, there's still a lot that's not known about them, and so we went in and used the processes of dendrogeomorphology, which means we were using tree ring data and chronologies to estimate the expansion rates of the crevasses in Devil's Half Acre and tell their story.
Devil's Half Acre is located on Carboniferous strata, so this means more specifically the Mahanguin Formation overlain by the Boss Point Formation, and these two interact in a special way that leads to gravity sliding, and there's huge gaping holes that appear within the rock, and this effect is emphasized by coastal erosion, since Fundy National Park is located in a megatidal coastal region, and so as the crevasses begin expanding closer and closer to the coast, they end up toppling off into the ocean.
Our research question is, what is the exact rate of expansion of the shale crevasses in Devil's Half Acre in Fundy National Park in centimeters per year?
So we chose trees that were visually affected by the crevasses, ones that were leaning into the crevasse or had roots spanning across the width of the crevasse or into the crevasse as well. We also took depth measurements and width measurements of all our crevasses. In total, we took 40 samples, including 10 chronologies, and at every site we also took notes based on the characteristics and surrounding area of the tree. So after we got our samples back to the lab, we first started out by mounting them all on wooden trays, and we began the process of sanding them. We used 6 different sanding belts of different grit sizes to sand them down so we could clearly see the tree rings. From there, we were able to measure the annual growth of each sample using a software called Telurbo. And from there, we were able to cross-date them using another software called Cofetcha. And this enabled us to be able to analyze our data.
So we began our data analysis by making a graph of the control chronology from the Devil's Half Acre, which is illustrated in black in comparison to the Point Wolf chronology, which is illustrated in yellow on the graph. And these two share very similar geologies, and they're very close to each other. So we were trying to see if they had similar patterns, and indeed visually they do. So from this, we concluded that our control was viable and we could do further analysis. So we analyzed all 40 of our samples, looking for overarching patterns, and we did find that around the 1930s and in the 1970s, there was an abrupt decrease followed by a long period of sustained suppression. So from this, we decided to create an average annual radial growth for 3 time periods, from the 1880 to 1930, 1930 to 1970, and finally 1970 to present. So this first graph, we did that for the controls, which is in red, and for the samples, which is in purple. And visually, we can see that there is a large difference between the two, but number-wise, the samples grew 25% less in the 1930s and 50% less in the 70s. So from this information we gathered, the estimate of when the trees were affected by crevasses was around the 1930s, which also means that the crevasses began expanding around this time. So we were able to measure the exact rate of expansion by calculating the number of years the trees were affected, so 91 years, divided by the crevasse width, and this gave us an average of expansion rate of 3.1 centimeters per year.
So after the 1930s, when the crevasses started to expand more, the roots weren't able to expand as they were supposed to, because where there was soil before, there was no longer soil, and that limited their resources, which caused the trees to experience a decline in their growth rate. In the 1970s, there was a spruce budworm outbreak, and this one was more significant than the one in the 50s, and it caused a much steeper decline among all the trees than in the 1930s. But the control trees, after some years, they recovered from that and their growth rate increased again. But the sample trees did not experience that. Their growth rate remained quite low, and then it stayed that way up until today. And that's, we're assuming, because they're continuing to be suppressed by the crevasses because their roots don't have that room. Our rate of expansion that we found is 3.1 centimeters per year, which is much lower than the 20 centimeters per year that Rutenberg predicted. And that could be because when Rutenberg was looking at it, they were only looking at short-term expansion events. And that could be caused by events like freezing and thawing, or a lot of rainfall or storm surges could cause an event like that. Whereas when we looked at it using dendrochronology, we were able to take into account those short-term events that could indeed cause periods of rapid expansion, but we were also able to look at trends that were affecting the stand as a whole, like climatic trends or disease. And this gave us a better picture of the relationship between the crevasses and the trees.
So in conclusion, by looking at the overall pattern in the tree ring chronology, we can determine that there is factors that affected both the controls and the samples. However, it is evident that the rate of expansion of the crevasses definitely affected the trees. The good news is that the rate of expansion, as Carmen mentioned, was quite low. And so due to this low rate of expansion, crevasses are more stable, and therefore bat hibernaculum is more likely to be able to be there for future generations, versus a faster rate of expansion would cause a fast overturn of crevasses forming and then disappearing due to erosion.